This video is about the ramp up to the rebuild of this engine. We're going to talk about some important considerations about tools, review the parts as they've come back from the machine shop, and talk about prepping those parts to start assembly. One of the most important tools I'm going to use in this rebuild is the torque wrench, and actually 3 torque wrenches for different torque settings. And the reason it's so important is that you need to make sure you torque bolts down to the correct torque value, not only to make sure there's adequate clamping and to make sure the bolts don't loosen up over time, but also because every single element in the engine that you're bolting together is somewhat flexible. You know, even aluminum, even steel, when you apply a load to it, it will deform a little bit. And when you crank down the torque, you don't want to overdo it or underdo it. So an accurate torque wrench is really important. Now, in Wayne Dempsey's book, he makes the point that before you start this project, you might want to get your torque wrenches calibrated. And I looked into this. I called a scientific instrument calibration house, and they said they could do my snap-on wrench, which is my highest torque wrench, but they couldn't do the 2 Craftsman wrenches like this one that I have. And just the snap-on wrench alone would have been over $100 to calibrate. So it made me think about, how could I calibrate it by myself? And I think you can do it quite easily. So one, you need to figure out, if you hold the torque wrench horizontally, how much torque would be applied just from the weight of the wrench. You know, I have to put some torque in with my left hand to keep it up. And you can figure out where that force applied by the gravitational pull on the wrench, the location where that's applied, by just figuring out where the center of gravity is. And you can do that by just finding the balance point. So if you know that distance from the center of the head to that balance point, and you know where you're going to apply a load on the wrench, let's say at the handle, you can figure out how much torque is actually applied and compare that to the value indicated by the dial. And so what that looks like, if we draw that out, is here's the torque wrench, here's the head, and here's the handle. And so you can figure out where your center of gravity is located, and the force of gravity that's going to act on that point is equal to the mass of the wrench times the gravitational constant. Here's the center of the wrench, center of rotation. And we can figure out, just by measuring that balance point like I just showed, what this length is. I'll call that little L. And then we can apply a known force here, F. And if you know that distance to F, let's call it big L, you can figure out the total torque being applied to the head of the wrench, which I'll represent with tau. So if we write that out, that total torque is going to be the gravitational force times little l plus the applied force times big L. So we can make a quick experimental setup to measure that. Now this isn't going to be perfectly accurate, but it'll at least tell us if the wrench is grossly inaccurate or pretty close, within a few percentage points. So here's my quick and dirty torque measurement setup. So I just have a bench vise, and I got a really big bolt that I could cantilever off the vise, and I'm holding 2 nuts in the vise, one tightened very tightly on the bolt so it doesn't slip, and the other one just to support the bolt over a greater length. And so I can apply a torque to the wrench, and you'll hear it click, maybe. There we go. It clicked. We'll do it again. And at that point, I should be applying the same torque that is measured on the little indicator here. And so on this wrench, there's a little dial gauge, and you can turn this knob and dial in how much torque you're applying. So right now, I have it on 45 foot-pounds of torque. And this is about 18 inches long. And so that's 1.5 feet. And what I can do to apply that force is put a bucket on here. And you can see I've made this kind of janky ridge. I took two pieces of coax cable and just wrapped them in electrical tape, and then bent the handle of the bucket so it will kind of seat nicely into the handle notch. And what I can do now is just add water until it clicks, and then weigh how much this bucket is, and I know the length over which that force is applied. So I'm going to lift up this bucket and try not to spill this everywhere. pour this in. And it should take more than half. So the bucket weighs about 40 pounds full. So over 1.5 feet, that'd be 60 foot-pounds. And we're trying to get 45 foot-pounds. So that's about half full. About 3/4 the way full that we hear the click. Start going a little slower. Because I want to stop it right after it clicks. Come on, click. Got me almost there. Oh, there we go. Nice. So it just clicked, and now we can measure how much this bucket weighs on this bathroom scale. And that weighs 34 pounds. So actually that 34 plus 15 is 49, and this said 40. This says 45. So yeah, so there is a bit more torque, and this is under reading. But we'll take another measurement at a higher level. The process also works for the small torque wrench. To add more weight, I choked up on the handle a little more. This one has a pretty pronounced click. There we go. And what's nice about this little one too is I can still use the kitchen scale to weigh it, which is a pretty accurate little scale. I suspect more accurate than a bathroom scale. When I ran out of water weight, I had to use my own. And so this actually worked pretty well, where I put the scale right under a little setback from the torque wrench, so I could step on it, it could weigh my weight, and then I could apply load to the torque wrench at a known point and measure how much load then was applied to the wrench when it clicked. So that actually worked pretty well and stayed pretty consistent with the measurements from the water weight to then switching to adding my weight onto the wrench. And the reason this works is that my weight is acting vertically, and what I'm doing is applying a vertical load in the opposite direction on the torque wrench. So the difference between my weight measured without any forces on the wrench, on the scale, minus the weight measured when I'm pushing on the wrench is the amount of weight actually put on the wrench. So here are the results from the torque wrench tests. And this was certainly a valuable exercise. So I set up this spreadsheet where I have all these initial values of measuring the mass of the wrench, the gravitational constant, what the length was from the balancing test from the pivot of the wrench to the center of gravity position, and then the length from the head of the wrench, the center of the head of the wrench, to where the load's applied. So then the rest of this table is showing what the indicated setting was on the torque wrench, how much weight was applied to the wrench at this application load point. And I just put this all in SI units first. So I converted the weight to mass and then figured out the total torque applied to the wrench and then converted that back to, I'm sorry, this should be foot-pounds. And so what the actual torque was applied, and then the percent error between what the indicated measure was relative to the actual amount of torque.
And so for the big wrench, at low values, and this is, I think, pretty expected, that at low values of applied torque, right at the end of the torque wrench's range, it's pretty inaccurate. And then you get up to higher levels of torque and it becomes within 10%. And so here are the plotted values of measured torque versus indicated torque and a trend line between them. And so the trend is pretty good between them. So the torque wrench is behaving pretty linearly. So the R-squared value is 0.99. But this equation, y equals 1.1 times x, this is valuable because what this enables me to do is multiply the indicated torque by 1.1 to get what the expected actual torque would be on the wrench. And so what this is saying is that the torque wrench reads about 10% low. So you add about 10% more to the indicated value, and that's the actual value that you're going to get. What's plotted here is how the percent error changed over the range of tests. So it's pretty high, so negative around 20% at the beginning, like I said, and then around negative 10%. The medium wrench was the least accurate, but it still had an R-squared value of 0.99, so it's a pretty linear behavior. And this wrench looks like on average it's about a 16% error, so about 16% more torque you need to add to the indicated value to get the actual value. And you can see here the error range from around negative 20 to negative 10 through the scatter. And then the smallest torque wrench was actually the most accurate, at least in the initial part of the range. So initially it was right around -2, -5%. And then as I applied more load and went through more of its range, it got less accurate. But again, here it's showing pretty good linearity. Again, an R-squared value of 0.99, so that's great. And again, I can calculate the actual torque by the indicated torque by just multiplying the indicated by 1.11, so about 11% error to get the actual torque. So what this means is that now I can use these equations, these fit line equations, to actually know with greater confidence what the torque is going to be. I think I would have been okay if I had just used the indicated torque. Maybe not for this wrench, the middle wrench or the medium wrench. That one's a bit less accurate, but for the large and small, they're both around 10%. And given my measurement system isn't completely exact, but one thing that indicated that it was pretty good is you can see here I go from measuring with the water buckets to measuring just using my weight and adding a force to the wrench and subtracting that from my weight. And you can see that the results stayed pretty linear. And that's good. That's indicating that my method, at least going from the water weight to measuring my weight, was pretty good. And then I saw a similar trend here where I used the kitchen scale up to 100 inch-pounds, which is a finer, more accurate scale. And then I switched to the bathroom scale. And you can see at this switch point, there's not a really big change in linearity. And so what that indicates to me is that the bathroom scale was pretty good. It continued on with the trends as the kitchen scale. Yes, there's going to be some error in every one of these measurements, in the length measurement of where the force is applied and the load measurement. But, they're still pretty good and they're within 10%. Of the indicated value, and given that the indicated value always read a bit under what actual was, I think then I feel pretty confident to use this calibrated value of adding about 10% to the indicated value to know the true torque value applied to the torque wrench. A really common issue with these engines is that they do leak oil because of broken head studs. The head studs screw into the block. There's 4 per cylinder. And what they do is they clamp, let me open this up, they sandwich the cylinder jug, which sits right here, and the head, which sits on top of it. And so it's quite common for these engines to break the head studs, and thus you don't get as much clamping pressure either at the bottom of the cylinder or the top, and you start leaking oil.
And the guy I bought it from, who's a Porsche mechanic, and I both thought this, the oil leak in this was probably from a broken head stud. But when I opened it up, what I had found is that the head studs had actually been repaired at some point in the past before I owned it. And whoever repaired it did it poorly. They didn't Loctite and or torque down the head studs tightly enough to clamp everything together. So over time, as the engine ran, they actually loosened up, and it created some spacing between the cylinder and the head. And so as the piston was moving up and down and the fuel was combusting, everything was chattering against each other. And what happened because of that is that the surface at the top of the cylinder, right here, got really marked up and chattered and all rough and became a bad sealing surface, as did the bottom of the head, where it meets the cylinder, on this sealing surface. Now this sucked, because all these, on one side of the engine, all the heads have to be right in the same plane with each other, because they all have to clamp down to the same level so the cam box can mount on top of it. Now, when one chattered and then you needed to machine this to make it smooth, to get a good sealing surface again, it means you have to remachine all the heads. So I had to take this to a machine shop and get a good amount of machining work to get the engine squared away. I used a shop called Circle Performance, which is in southern Massachusetts. A guy named John runs it, and he did a fantastic job. He was great to work with, and I'd highly recommend him. He's super knowledgeable and has built race engines for years and years and years. But what we ended up doing to fix this problem was, first he had to remachine all the top surfaces of the cylinder jugs. And he had to remachine all the sealing surfaces at the bottom of the heads here, and make sure they're all level, all the same height, what's called the deck height, so they can clamp down together. Then I wanted to do some performance upgrades as well. One more thing about what John did too is we replaced the valve guides. So those are the guides that allow the valves to go up and down. They sit in the head right here. And they open up over time and leak, and they're a common source of oil leakage. So it's pretty common to, when you do what's called the top end of an engine, to redo the valve guides so they don't leak anymore. So John did that on all 6 heads. But then also I wanted to increase the performance of this engine. 911 SC engines made about 180 horsepower when new. And in today's standards, it's pretty anemic. If I compare it, actually, if you look behind me, to this guy, that's a 964, that makes over 250 horsepower and is a very comparatively fast car. So I wanted to make a hot rod that was that provided better performance and that I could use as a track car and kind of beat on. So I didn't take the 964 on the track, because that's actually a daily driver. So we decided to do a few performance upgrades. The first was we changed the compression ratio of the pistons, and this is a non-trivial task if you're thinking about rebuilding your 911 engine. The reason is that the original cylinder coatings that Porsche put in these SC engines are not compatible with aluminum pistons. My understanding is that the rings will just eat into, if you put new piston rings in, they'll eat into the cylinder walls. So we had to send these jugs out, and they got recoated with Nicosil, which is a great coating, really robust, and allows you to mix and match different pistons. So I also bought new pistons from Carrillo or CP. John and I had a lot of discussion back and forth about whether to use CP or JP pistons. And my recommendation, if you're doing this, is do your research. I read all the forums, and I actually called JP and CP and talked to their folks. And I also connected with a guy named William Knight. He runs a shop called William Knight Performance, and he's quite well known. If you look on the Pelican Parts forum, there's one called like William Knight's a Hero or something. But quite well known for making great race engines. And he convinced me to go with Carrillo CP pistons. So I think that was a good choice. And we ended up upping the compression ratio to right under 10 to 1. It's about 9.8 to 1. When you go to 10 to 1 or higher, you can end up getting a non-uniform flame front when you combust the fuel. So a regular 911 head, and you can see it right here, and let's see, I think it goes like this. I apologize if this is upside down, but the point here is that a conventional SC head has one spark plug outlet. Now you can actually machine a second one into the head right here, and you could do what's called twin plugs. And the reason they do that is that when you go to higher compression and the piston comes up higher, this top part of the piston actually blocks off the flame front as you combust the fuel. So if you ignite it on one side, you don't get a good burn of the fuel and good expansion of the gases on the other side because there's not really room for the flame to flow. So in high compression engines, it's common to put twin plugs in so you can spark both sides and get a really uniform flame front. And that's actually what they do in a 964. This was the first, as far as I know, the first factory twin plug 911. I didn't want to do twin plugs because it's quite expensive. The extra machining, you have to have another distributor, a 12-plug distributor. It was just an overkill for me. So I just went with higher compression pistons at the max compression I could get away with before worrying about a non-uniform flame front. So that's why we chose those. And then I also wanted to hop up the cam a little bit to make more of a race engine, have higher duration or higher lift, so it would push the valves down more, and higher duration so you can get more gases in and out. And one thing that's important there, if you want to go to a high lift cam, you can't use the stock 911 pistons because they don't have as big enough cutout for the clearance of the valve as it goes in and out. So that's another reason to upgrade pistons. But again, a word of warning that this is totally a can of worms if you open it up, and it's a black hole of in which to throw money if you want to do upgrades and upgrades and upgrades. But I want to do a hotter cam, higher compression pistons in order to make more power. Now the cam I decided to go with it was provided by a company called Webcam. Be careful when you Google webcam, you might get something else. But if you do webcam camshafts, you'll find the right place. What Webcam will do is you can buy new camshafts from them, or they'll regrind your current ones. I actually went with a regrind because I didn't really need my old camshafts sitting around. And they were somewhat worn anyway. Not bad. There weren't no flat spots or anything really on the lobes, just some scratching. The grind I ended up going with is called the 464 465 grind. And it's based off an old 911S, I think from the 60s cam profile. It provides a higher lift, so that means the cam lobe is actually taller, so it pushes the valve in further, and in a longer duration than the stock 911 SC cam. And both that lift and duration enable you to get more air into the engine. So I did a lot of research looking at what cam grind would be best for this car. There's a lot of different grinds available, but I decided on this grind because of one, feedback from William Knight, and two, what I read online, three, conversations with Webcam saying that this was a very popular grind for the type of application I was looking for, and also the torque and speed profile that the engine would have because of this cam. I wanted something flexible enough that I could drive it on the street and I didn't have all my peak power right at the top of the RPM range. I wanted it more spread out. And so this cam gives a nice balance of higher power certainly than you can make with a stock cam, but pretty good low end torque still, so you can drive it on the street. The last piece of the puzzle to hot rod this was thinking about the injection system. So with the stock CIS fuel injection system that came on these cars, you're kind of limited in how much power you can make because you're limited in how much air you can get in. What a lot of people don't realize is that what limits the power of an engine is not how much fuel you can put into it. You can pump as much fuel as you want. It's how much air you can get in there to combust the fuel.
And so the CIS system doesn't allow a lot of air and thus doesn't allow a lot of fuel. And you're limited to making, I don't know, estimates differ on what you read online, but I think it's about 50 horsepower more that you can make. So I wanted to make more than that, and I'm actually going to switch this over to carburation, which is an older technology, but it allows you to dump a lot more air in and a lot more fuel. It isn't as efficient, so my fuel economy will go down, but again, this is not ever going to be a daily driver car, so I wasn't too worried about that, and I care more about making more power. So with all these upgrades together, with the higher compression pistons, with the hotter cams, and with the carburation system, I'm hoping that this is going to make around 280 horsepower instead of the stock 180. So that's going to make this a pretty quick car. It'll be more power and quite a bit lighter weight than a 911 964, like the one behind me, and hopefully be a pretty great track animal. If you're doing this at home, be very careful to keep everything clean. I actually had a sheet of poly over all these parts before this, and the first steps I'm going to do is clean up all the sealing surfaces on this block and other parts of the engine to get it ready. One thing that was quite helpful to me as I was setting up this project was going through Wayne Dempsey's book in the engine rebuild section and looking at, he does a nice job in laying out what you're going to need for each section. So here's all the tools for section 1, preparation cleaning, and then as you start building, here's a crankshaft assembly. He says all the tools and materials and stuff you need. What I did is I actually built up a spreadsheet that has all these things listed on it. So I'll zoom in over here. And so I broke it up into categories by the sections that Wayne set out for the different stages of the motor rebuild. And what this enabled me to do is just keep track on what I have already and what I needed to order and where to order it. If I need to get it, like here's barrel stud nuts from Pelican Parts, here's the part number. This, by the way, is not an advertisement for Pelican Parts. I have no affiliation with them. I don't buy all my parts from them, but I do buy a good amount from them, and their customer service has been good in the past. So this has been a helpful resource to just get everything ready for the project and make sure I have everything I need. And it's something I'd suggest if you're doing this project yourself. An important part of prepping the engine is making sure it's clean. And so there's, I guess, different levels of cleanliness that you want to achieve. This block was cleaned in a large parts cleaner by my machinist, but it's still good to go through it and make sure there's no dirt or particles sticking to the block. A good tool you might want to use is brake cleaner if you have some greasy stuff, as well as having these clean wipes, Kim wipes, which are scientific instrument wipes and do not leave fibers behind when you wipe things off. So I've noticed just going through this, there's like, if you can see it right here on this surface, there's a bit of grease, and you can hit that with some brake cleaner, wipe that off. Just grease and dirt, because this is on the outside of the block, which is out in the elements. And you can see, you can get that stuff off. So I'm trying to knock off all the loose stuff. I'm trying not to use the brake clean much. This is nasty stuff. Not good to ingest, not good to inhale. Probably, I'd recommend using gloves probably to do this. But I'm trying to use it sparingly. On the rest of the block, what I'm using is I've got some isopropyl alcohol in this little bottle, and where I don't need as much dissolving capability in a solvent, I can just use alcohol and clean things up. And then the other important part of what I'm doing is just going through all the sealing surfaces and going over all the sealing surfaces with a straight razor blade. The block still has residue on it from when it was last sealed, and if you scrape along the edge, let's see if I can pick up some. If you scrape along the surface, you're going to see it when I zoom in on this, where I'm scraping. So you scrape along the surface, and you can see there's this ridge of gunk that's coming off. That's just all the old sealant. So what I'm doing now is going through the whole thing, going over all the sealing surface. I've already done this side, just making sure it's smooth, making sure there's no sealant that could affect the surface. What's going to happen is that when this thing's bolted together, is that all these through holes have long bolts that go through both sides of the block, and the whole thing is clamped together with these bolt holes. And so these holes are distributed to distribute uniform pressure over all the sealing surfaces. And really, wherever you see something flat, the block is sealed. So it's really important that there's no high spots of gunky sealant or dirt when this is clamped together, so you can get that nice sealing surface. So you need to make sure it's clean and flat. One other important tool I'm using a lot is just canned air. You can get this at Staples, and this is much cleaner than shop air, and you can blow off all the gunk you're scraping off. It's also important to remember that like stuff is falling down into the cavities in how the block is oriented as it is now. When I'm done, I'll have to tip it up and turn it in all different directions and really try to blow out all the remaining junk. I'm not going to bore you with hours and hours of doing this, but buckle up. It takes a long time, but be patient. And it's like measure twice, cut once. You don't want to have to take apart a block after you've rebuilt it because it's leaking. So it's worth putting in the time now to get everything perfectly clean and ready for sealing. Another really valuable tool I've been using is a set of thread chasers. So you can see that a number of the threaded studs are kind of rusty, and it would be difficult to thread a new bolt on. So this set, I found this online. I had to shop around. I didn't just buy this from Amazon, but here's a set of thread chasers, and it's both for internal and external threads. And what this set does is it allows you to run a nut. So I'll do it on this one. Allows you to run a nut down the thread, and what I've been doing is just putting a little bit of lubricant on it, which one I think will help preserve the chaser, and two helps catch rusty particles so they don't go everywhere, and you can just wipe them up after. But I've just been running them down the thread really gently, and I've been using this little driver because it's faster, but don't just whale it on there, because when you run to the end of the threads, you don't want to start threading them. Then you take it off and just clean off the threads and clean off all that rust. But what these do is they'll enable you to put a nut on or a bolt in much more easily when you go to reassemble the engine. It's really important to use these instead of a tap and die set, because you're not trying to cut new threads. You're just trying to clean them up. And so this maintains the same thread dimensions as they originally had. I'm going to do these on the head stud holes too. So here's one of the head stud holes. Here's one of the male threads for a female hole. And this is good because it just helps you get out all the gunk from the thread sealer that was used originally. So you can just run that down to the bottom really gently and back out, and it'll take out any little gunk. One of the trickiest parts of cleaning the case that I've found is getting these little oil squirters clean. So these are little orifices that are in the block that shoot oil underneath the piston to cool the skirts. So what I've done to clean them out is you can, on this side of the block, you can squirt brake clean into the oil passage, and if you pressurize it, you can force the fluid through. What I've had to make is a little plug. So this is just a bolt with some electrical tape on it that I can put in the hole to seal off that channel. And then you can take an air hose from the backside and pressurize it, and hopefully you see some fluid come out. Yeah, so it's squirted out and it's not clogged. In the other case, what I did is I took just a regular Phillips screwdriver like this, and if you wrap electrical tape around it, you can actually stick it down this hole and plug off what would be a leakage port in order to pressurize the channel and purge the oil jets the same way.
When I got this parts washer, I hemmed and hawed a little bit about what sort of solvent or detergent I should put in it. There's a lot of like grease cutting, grease eating type solvents that you can put in here that are water based. I decided to go with a non-water based solvent using mineral spirits for a few reasons. One, I didn't want any corrosion on the parts after I brought them out or any residue. And what's nice about the mineral spirits is it does evaporate after a little bit of time, and it leaves the parts cleaner, and I don't have to worry about corrosion. The second was fumes. What's nice about these odorless mineral spirits, and I just got these at Home Depot. I got 10 gallons of them. Is it's really not bad sitting here. You can smell it a little bit, but it's nothing like other solvents like gasoline or heating fuel, heating oil. I read a bunch of forums about what people used, and you can use gasoline or diesel, but it's going to stink a lot worse, and it would be tough sitting down here. This is also in my basement where I don't have a lot of great ventilation. So this worked out quite well. One thing to note though, if you can find bulk purchasing of mineral spirits, you'll save yourself a lot of money. The mineral spirits was actually more expensive than the parts washer itself. Another tip is that you need enough fluid in here so the pickup of the pump won't cavitate and can actually suck the washing fluid up and squirt it out. I tried with 6 gallons at first, and it was almost able to bring it up. I could tip the parts washer a little bit and it would bring it up, but I ended up putting 10 gallons in here. The tub can hold 20, but it seems like 10 is a pretty good compromise, because when I put the parts tray in here, it's still above the fluid line, but the pump has no trouble picking up the fluid, so I'm pretty happy with this. I've never owned a parts washer, but oh my god, this saves so much time and effort compared to if I was trying to do this manually with just like brake cleaner and asphyxiating myself with brake cleaner to do all this cleaning. Oh, another hint that I'd give anybody doing a project like this is label your bags of parts and keep your parts with the bigger engine hardware they go with. Every single part in this project has a little baggie with the specific fasteners and washers and stuff that came off when I did the engine disassembly. So, you know, you can see again with the chain covers. And I think this is going to save me a lot of time in the long run, because I'm getting new hardware for the case. So I'll replace all these washers and all these nuts, but I don't necessarily know which size nuts and which size washers go where in the assembly, and this will be extremely helpful in letting me do that, because I can just lay out the old ones and then lay out the new ones and compare and replace.
So I've let the valve chain covers soak for about a week now, and they're pretty good. You can see the dirt's you can probably see the dirt's just flowing off them now. So these are really dirty. This car was in the Northeast, and it unfortunately saw a good amount of salt. Luckily it was a galvanized body, so it didn't rust very much. And there's really no rust on the body. I also bought this brush. I got this at AutoZone, and yeah, it's good for just, you know, scraping off the extra junk. I'm pretty happy with how the soak came out actually on these. There's some like really caked on greasy stuff that I can see now over sitting for the week has really loosened up and is kind of washing right off. So this was definitely a worthwhile investment, and all the other parts that are all greasy and oily and stuff are going to be washed in this thing as well.